In this episode, we're going to be straying from our usual vlog content a little bit. We asked you, the viewers, for some questions on our YouTube, and you gave us plenty of great ones. So we're going to do a bit of a Q&A session. Let's get started. Our first question comes from Ryumoto, who has asked, would love to see some more coverage on the struggles of tuning for drivability on ITBs or individual throttle bodies. That's actually a reasonably big topic. There's a little bit to cover, so we'll start with the fundamentals that in a conventional single throttle and plenum arrangement, we're typically tuning on an aftermarket standalone using speed density, where we have manifold absolute pressure as the load axis for our fuel and our ignition tables. That works great when we've got a single throttle and plenum. When we've got individual throttle bodies though, our manifold pressure signal is first of all harder to get. We need to get that manifold pressure signal from all of the throttle bodies, 4 throttle bodies on a 4-cylinder engine, for example, and we need to have a balance tube basically to give us that signal averaged out. Even when we've got this though, we still can't do a really good job of our fuel tuning using that map signal. And the reason for this is on ITBs, the map signal is no longer really a good indication of engine load. So instead, we tune on alpha N, which is where we're using the throttle position signal as the load axis for our fuel and ignition tables. So that's the key one there. There are a few other intricacies though. If your ECU allows, what we also still want to do is incorporate that manifold absolute pressure signal from our balance bar into a background fuel compensation. So essentially, to try and make it really simple, the principle here is that if we double the manifold pressure, we need to double the amount of fuel or the mass of fuel being delivered in order to maintain the same air-fuel ratio. And that's one of the principles behind speed density anyway. Now we still have that same aspect going on with an alpha N system. And the reason for this is that depending whether we're going uphill, we're driving on straight road, or we're going slightly downhill, we can actually find that our manifold pressure signal varies even at a fixed RPM and throttle position. So what this will basically transpire to be, if we aren't using that background compensation for our fuel quantity using manifold pressure, we're going to find that depending whether we're driving uphill, flat or downhill, we're going to find that we see variations day to day and moment to moment in our air-fuel ratio. It's very difficult to get really consistent air-fuel ratio if you don't have that background compensation going on. Most ECUs will allow this, but it's just a case of building the balance bar arrangement where we're taking a map signal from behind each individual throttle body and running that into a balance tube, running that to our map sensor. So that's the first thing. If we haven't got that going on, we're going to really struggle to get good consistent fueling. Now the other aspect to keep in mind here is the way the throttle body works. And while it isn't an individual throttle body here, I've got this Bosch drive-by-wire throttle which still illustrates the point. What we need to understand here is that the airflow through the throttle body as we open it from completely closed to fully open is really non-linear. What I mean by this is that when we first crack that throttle open, maybe the first 5 to 10%, we get a really large increase in our airflow through the throttle body. On the other hand, if we've already got the throttle open maybe 80% and we open it another 20% to wide open, we're going to find that the actual airflow from 80% to 100% doesn't actually change dramatically. So we need to take this into account when we are setting up our fuel tables and our ignition tables in our ECU. And this is really about our breakpoints that we use for our load axis. So instead of maybe having breakpoints every 10% throttle opening, generally I'll start with 0, then step 2, 4, 6, 8, 10. Once we get up to 10%, we can get a little bit coarser, maybe 10 to 15 to 20. Then we can step in 10% increments. So we're getting good resolution down near closed throttle, and that'll allow us really good control of the fuel delivery at very small throttle openings. Once we've got those basics set up, really it's no different than tuning a conventional speed density based ECU. We're just going into the center of each of our cells and adjusting our fueling until it matches our target. And then of course we're doing the same with our ignition timing, trying to tune that to MBT or where we find the knock threshold. Obviously if the engine is knock prone, we need to leave ourselves a little bit of a margin so the engine isn't suffering from knock. Everything that I've covered there so far is really related to naturally aspirated engines, and it's also possible to have individual throttle bodies on turbocharged engines. Nissan did this, just for one example, on both their RB26 as well as the SR20 DET fitted to the GTIR Pulsar. This adds another layer of complexity. Just like the naturally aspirated engine, we still need to use throttle position as the load axis for our fuel table. However, the fueling that we're going to require at, let's say, 100% throttle, 5,000 RPM and 10 PSI of boost is going to be very different to the amount of fuel we need to deliver at the same RPM and throttle position and 25 or 30 PSI of boost. So what we need is another way there of adjusting our air-fuel ratio based on the manifold pressure. So we've basically got 4 dimensions to consider. We've got our throttle position, we've got our RPM, we've got our manifold pressure, and then we've got obviously finally our fueling. Now, there's a few different ways of dealing with this depending how the ECU operates. The modern ECUs that use volumetric efficiency or VE based tuning actually make this pretty straightforward. The VE table, the fuel table itself, isn't really a fuel table, it is a volumetric efficiency table. It's defining the volumetric efficiency of the engine. Now, once we've got that, we're going to have another table which will be our air-fuel ratio target or lambda target table. With this table, instead of using throttle position as our load axis, we're now using manifold pressure. So this allows us to set our air-fuel ratio targets to the realistic targets we want to be achieving based on manifold pressure. And then simply we're going to tune our throttle position based VE or fuel table to achieve those targets. And we're going to find that if we start at wastegate pressure, the minimum boost pressure we can achieve, tune our air-fuel ratio targets to, or tune our VE table, I should say, to achieve our air-fuel ratio targets. And then we start stepping up the boost. We're going to find that everything just kind of magically seems to work and track. Now, this works nicely until we start pushing the turbo to the point where we're really building up exhaust back pressure and the efficiency of the turbo and the engine airflow drops off. And we'll find that once we get to that point, the air-fuel ratio starts to track richer than our target. We can work around this with a compensation table just to remove fueling in those areas at higher boost and higher RPM. And this works really, really well. It's a nice, clean way of doing it, as long as we understand the principles behind what's going on. So thanks for your question there, Ryomoto. Hopefully that's answered your question and given you a little bit more insight into individual throttle bodies. Our next question actually follows on a little bit from that previous question. This is from Sergeant Will Kill You. Great name there. Why is speed density considered better to tune than MAF? This is actually a common question I get asked, and the reality is it's not better, it's just different. What we see is a lot of tuners who have grown up tuning using a aftermarket standalone ECU which doesn't use a mass airflow sensor. Basically, they get comfortable and familiar with tuning a speed density based fuel model. Now, there's nothing wrong with that. It can work really, really well. However, most OEs, definitely not all, but most OE manufacturers instead use a mass airflow sensor. So the principles behind the two are that a mass airflow sensor physically measures the mass of air passing through it into the engine. Now that's really important because if the ECU knows what mass of air is entering the engine and it knows what size injectors are fitted, or to put it another way, what mass of fuel will be delivered for a given pulse width that the injectors receive, it can calculate really accurately how much fuel to deliver in order to achieve a target air-fuel ratio. So when everything's calibrated correctly, a mass airflow sensor can potentially deliver more accurate fuel delivery because it is directly measuring the mass of air passing through it. Now yes, there are some caveats there, particularly around transients or sharp changes in throttle position or RPM. The mass airflow sensor can have a little bit of lag or latency, and there's ways that OEs get around this by using both a mass airflow sensor and a speed density subsystem based on the operating parameters at the time. GM are a classic example of this with their LS range of engines. This is exactly what they do. I'm digressing a little bit though. I just needed to explain how the mass airflow sensor works. Now the speed density principle, on the other hand, we get rid of that mass airflow sensor, and instead the mass of air entering the engine is calculated using the ideal gas law. So that's why we have manifold absolute pressure as our load axis. And this can also work really well, but because the mass airflow is calculated, it does provide us with a little bit more room for error. And that's why we'll see quite a lot of compensations and correction tables in a speed density based ECU. Mass airflow basically just does all of the heavy lifting for us. For example, we quite often get asked questions about changing the tune for changes in altitude on a speed density based system. Doesn't matter on a mass airflow based system because the mass of air is physically being measured again. As we go up in altitude, the barometric air pressure drops, the air density drops. We've got less massive air moving through the mass airflow sensor. It's detecting that, so it's reporting the lower massive air straight to the ECU, so everything just works. To get onto the specific question though, I think the problem is that a lot of tuners choose to get rid of the mass airflow sensor and revert to speed density simply because that's what they're used to. And that can actually provide you with quite a lot more work though at the end of the day. Let's have a quick look at a couple of examples in the laptop software here. Let's start by having a look at a conventional speed density based ECU, in this case the Adaptronic modular that we've got running on our Mazda FD RX-7. So this is our VE or fuel table, and we can see graphically we've got the fuel table represented up here. Down the bottom we've got our three-dimensional grid of values. The vertical or load axis there is manifold pressure, horizontal axis there is RPM. Now what we have to do is tune each of the cells inside this table to achieve our target air-fuel ratio, and you can see we've got a lot of cells in that table. It's going to take a lot of time, it probably doesn't take a rocket scientist to figure out, in order to access each of those individual cells and adjust the values until we've got our target air-fuel ratio. So the tuning process on a speed density based ECU is by necessity relatively time consuming. On the other hand, let's jump across to the HP Tuner's VCM editor software. Here we've got a map loaded up for our Holden Commodore, which runs a GM 6-litre LS2. It's actually an L98 engine, but let's not split hairs. And we'll have a quick look at how this is set up. So we'll start by heading over to the airflow tab here, and we'll have a look at our mass airflow sensor calibration. So we'll click on that, and we can see what that looks like inside of the engine control module. And we can see we've got a grid of numbers up here, and the output from the mass airflow sensor is actually a frequency. So that's what it outputs back to the ECU or engine control module, and this table then converts that into mass airflow in grams per second. So for example, if we were seeing a value of 3,300 hertz into the ECU, this would equate to 9.61 grams per second of airflow. So the key to the whole thing there is making sure that this calibration is accurate. If the calibration isn't accurate, everything else goes out the window. But fortunately, getting that accurate isn't too difficult. Now, once we've done that, the fuel tuning in the GM range of ECUs is actually straightforward. There's essentially two modes. The engine control module is either in closed loop, where it's targeting 14.7 to 1, or it's an open loop, or what GM refer to as power enrichment, which is where we're targeting a specific air-fuel ratio. When it's in closed loop, there's nothing for us to do as a tuner. It's just targeting 14.7 to 1. It knows what massive air is entering the engine. It knows what size injectors are fitted, so it just can output the right pulse width to get our target air-fuel ratio, and it can do it really accurately. When we move into power enrichment, this is where we want to target a different air-fuel ratio, because if we were targeting a stoichiometric air-fuel ratio at wide open throttle, we're not going to end up achieving maximum power, and also our combustion charge temperature is going to end up increasing. Let's head across to our fuel tab and we'll see how that's dealt with. And we are here on our fuel power enrichment tab. There's a bunch of parameters here. One of the key ones is our hot throttle table, so we'll open this. In some engine control modules, there's a hot and a cold table. This only has one, but essentially defines at what throttle position versus RPM the engine control module will transition from closed loop to power enrichment. Once it is in power enrichment, we obviously need to target a specific air-fuel ratio. Let's have a look at that. This is our power enrichment EQ ratio or equivalence ratio gas. So we'll open that table up. So here, instead of that big three-dimensional table of numbers we saw in the aftermarket standalone, here we've got a simple two-dimensional table versus our engine RPM. And this is simply our target equivalence ratio. Now the problem with this is equivalence ratio doesn't make sense to a lot of aftermarket tuners, so we need to convert that into something we understand. Let's just bring up our calculator here and we'll see how we can quickly and easily do that. So all we want to do is take our equivalence ratio. So at the moment in this table, it's set up very simply one fixed value. That wouldn't be typical, but let's just go with that, 1.176. Now first of all, we need to convert from equivalence ratio into lambda. So we can do this by using the little inverse function. Equivalence ratio is simply the inverse of lambda. We'll click on that and it gives us our lambda target. So this table simply means that we are targeting 0.85 lambda. Now, a lot of tuners don't work in lambda units. That's fine too. We want to go one step further and convert this into air-fuel ratio units. We simply multiply by the stoic air-fuel ratio for the fuel we're running. In this case, pump fuel will multiply by 14.7. So that gives us a target air-fuel ratio in power enrichment of 12.5 to 1. So the reason I wanted to go through this is that if we are running a mass airflow sensor, provided it's calibrated accurately, there's so little work for the tuner to do in terms of delivering the correct amount of fuel. All we need to do is ask for a specific air-fuel ratio, our target air-fuel ratio, and the engine control module can deliver it. Much, much quicker, simpler, and easier than tuning a speed density fuel table. Now, the other misconception is that a mass airflow sensor by necessity causes a restriction to airflow. Now, there can be some truth in that, particularly with the older Gen 3 LS1, just for one example there. The airflow meter was restrictive even in stock form, and removing the airflow meter and performing a speed density patch would generally give us somewhere in the region of maybe 15 to 20 rear wheel horsepower with basically no other changes. These days though, we can't say that every mass airflow sensor is restrictive, and particularly with the later GM engines, there was no power to be gained in removing the mass airflow sensor. They stepped up to a larger size mass airflow sensor, it just simply didn't provide a restriction. So that simply means that you can't always expect to gain power by removing the mass airflow sensor. One last point though, in some instances I definitely would choose to eliminate the mass airflow sensor. In some cases, if we're adding forced induction to a naturally aspirated engine, we're going to exceed the airflow measurement capability of the factory mass airflow sensor. Now there can be workarounds on that, but at this point we may be considering changing to speed density. And the other aspect I'd consider there is if we're running a very large aggressive cam with a lot of overlap, this can play havoc with the mass airflow sensor, particularly at idle and light throttle. We get a lot of reversion pulsing, and essentially this causes air to be blown back out through the mass airflow sensor, and it kind of gets measured twice. So this can cause problems with our fuel accuracy, particularly at idle. So thanks for that question. Hopefully that's given you a little bit more insight into the differences between speed density and a mass airflow sensor based ECU, and why you can't really clearly say that one is superior to the other. Both have pros and cons. It's all about understanding those and making the decision that's right for you and your application. Our next question comes from Snives Z32, who has asked, how do we program the spool up mode used in launch control applications? It's my understanding that you retard the cam and retard the ignition for turbo applications. How much of each? Is there a PID closed loop to control cam and ignition once it's reached target boost pressure, and how do you tune those parameters? What aftermarket ECUs support this? I know my E92 has this feature in the stock ECU. Okay, good question there. It's a difficult one to answer completely on account of every ECU is a little bit different, and what you're trying to achieve will also affect the way you go about doing this. So I'm going to take a specific example here, which is in a drag application. So this is quite unique, but it does really highlight exactly how all of this works. In this particular application, we're going to ignore a variable cam control though, and instead we're going to focus on the way the launch control strategy works in terms of the fuel cut, or ignition cut I should actually say, and the ignition retard. So I'm going to give you an example here from a Mitsubishi Lancer Evo 9 drag car that we built, as affectionately referred to as Project DS9, and this at the time we were running it held the world record for the fastest late model Mitsubishi Evo four-wheel drive. It ran as quick as an 8.34 at 169.7 mile an hour. It also ran on a really small tyre, given the power it was producing, about 1,001 wheel horsepower, which was part of our class restrictions. So managing the power was really critical. When we're running a large turbo on a small engine, in this case it was a 2.2 litre stroke 4G63 running a Garrett GT 4202 turbo, the problem is getting the turbo onto boost on the start line. Once we leave the start line, we're clutchless shifting with a dog engagement gearbox, so the turbo doesn't tend to fall off boost too much, but it's getting it there in the first place that is the key. So let's have a look for a start at the data logging from our Motec M800 ECU, and we'll see what's going on here. So our top graph here, we've got our engine RPM. So this point here is where the driver is staged and on the two-step limiter. So we can see that the RPM is bouncing around a little bit, but basically sitting at about 7,300 RPM. And it's really nice and stable through there. You can see that that line is pretty flat. That's really important to get consistent launches. You can see that the driver's foot pedal or throttle position is sitting the whole way through there at 100% throttle. And what's interesting though is to look at what's happening with our manifold pressure. Actually, if we zoom out a little bit and we look at the point where the driver has first gone to full throttle, around about this point here, we can see that we've got very little boost. This is absolute boost pressure. So we've only got about 30 kPa of positive boost, even though we're already at 6,800 RPM at that point. So 30 kPa, that's not going to get the car off the line. So all we can see here is in our bottom graph, we've got our ignition advance, and we can see that as soon as we go onto the two-step, there's a switch which basically brings that on. We can see that the timing drops, and it actually retards all the way back down to minus 7.5 degrees at this point. And you can see as the timing is retarding, we're starting to see that boost climb up. So by the time we're here, we're at about 230 kPa, 130 kPa of positive boost, so we're around about 19 psi at that point. Our target for this particular run was around about 250 kPa of absolute boost, which is 150 kPa positive, around about 22 psi, and we can see that we reach that point here, or 240, it moves around a little bit, and at that point the boost pressure stays relatively flat. And we can see that our timing is actually moving up and down, and we're using the timing in order to help control the boost pressure. So that's what happens there. At this point here where we see this vertical line in our ignition timing, that's where the driver drops the clutch, it releases the two-step limiter, we see the timing reverts to our normal timing, and we start seeing the RPM rise, and that's where the car actually launches and starts going down the drag strip. So this is one of the keys to tuning launch control on a small capacity engine with a large turbo. Let's have a look into the Motec ECU Manager software and see what all of that looks like. Now in the ECU Manager software, there are a variety of different ways of achieving the same aim, so nothing particularly set in stone about how we must go about this, but we'll go through a few of the settings here. First of all, we go to the Adjust menu, we come down to our digital input functions. We have one set up here called Dual RPM. So Dual RPM limiter, two-step limiter, everyone's got a different name for it. We'll have a quick look at our parameters here. So the key parameter here, or two key parameters, are the low RPM limit. In this case, 7,200 RPM, this is actually from a different run. So this sets the RPM limit for our launch control strategy. In the data log we just looked at, we all remember it was 7,300. So that's important. We're going to adjust this based on the track conditions. As we raise the RPM, we tend to provide more energy to spool the turbo, so it's easier to make boost, but it can also be harder to get the car off the line. So this becomes a bit of a balancing act there, and we tend to find a sweet spot for where the car will launch well, and then maybe manipulate that a couple of hundred RPM each way, depending on the track conditions, whether it's really sticky or the track's a little bit loose and slippery. The other aspect below that is our RPM rise rate. So this is a function particular to the Motec 100 series ECU, and essentially what it does is it defines how quickly the RPM will be allowed to rise once we get off that two-step limiter. So this is kind of allowing us to make sure that if the car breaks loose as the driver sidesteps the clutch, that it's not just going to run straight up onto the engine RPM limiter, which in this car is about 11,000 RPM. It controls that, and in this case allows the RPM to rise at a rate of 5,000 RPM per second. So we can kind of use that as a bit of a passive launch control strategy, or sorry, passive traction control strategy, I should say. And again, we tend to manipulate that a little bit based on the track conditions as well. So that's our RPM limit. Now, another key aspect to consider is if we want really effective launch control, we really need to be using an ignition cut strategy. Now, what this does is, as its name implies, it cuts the spark to individual cylinders in order to control our RPM on that two-step limit. And when this happens, the injectors are still pumping fuel into the engine, so we're getting a full combustion charge of unburned fuel and air being passed out into the exhaust manifold. Now, if we use this next strategy, which we'll look at in a second with our ignition retard, this can cause the combustion event to happen very late in the engine cycle. It continues out into the exhaust manifold, essentially igniting the unburned fuel and air, creating combustion in the exhaust system itself, and that is what drives the turbocharger. The important thing here is because the combustion is happening in the exhaust, it's not actually creating engine power, which would obviously increase our engine RPM. So that's the key to a two-step launch control strategy, and the amount of energy we provide to the turbo is controlled by two things. First of all, the RPM, as I've already mentioned, and secondly, the amount of ignition retard we're using. Before we jump onto the ignition retard though, I just want to add a little caveat here for safety. Just understand that an ignition cut limiter can be very, very dangerous on some engines, particularly engines with a fragile valve train. The SR20 is a really good example where they've got a very heavy lifter, a rocker I should say, in the cylinder head. The ignition cut can provide large pulses in the exhaust manifold, which can actually bounce the exhaust valves back off their seat, and this can end up potentially, in the SR20 case, popping the rockers off and causing all sorts of damage. So you need to be very mindful, and there's often some pretty extreme changes we make in the cylinder head to cope with an ignition cut limiter and making sure that the engine is going to remain reliable. So if in doubt, stay away from an ignition cut. Use a fuel cut. It's much safer on all engine types. However, fuel cut will not work as well for this strategy. Now that we've got the safety aspect out of the way, let's jump back into our laptop software, and what we'll do now is we'll have a look at our ignition main table. So this is our ignition table here, so our actual ignition timing when we're not on our two-step limiter. But if we come back up to our adjust menu and we go to our ignition and come down to compensations, come down to our user compensation 1, and we can see that this is a three-dimensional table. Our horizontal axis here we've got set up depending on whether the two-step limiter is active or not. Then our vertical axis here is our manifold absolute pressure. So we can see that in our column 1, this is when our two-step limiter is active. We see the amount of retard that we are using. And we're going to start obviously around about atmospheric pressure here, and I'm not using a lot of retard initially. If we use a lot of retard, you can see we've got maximum values in there of -32, so we're pulling 32 degrees off the table values. If we use that right from the point where we enable the two-step limiter, the engine's going to become really doughy and it will actually be difficult to actually get the engine up onto the two-step RPM limiter in the first place. So that's why we start with a limited amount of retard. Once the boost starts to build though and we move up this table here, we can see we're using more and more retard. By the time we get up to 190 kPa, we've got 32 degrees being pulled out of the table values. So that's quite aggressive. That's why we were seeing the timing go down below zero. So the actual spark event was happening after top dead center. Now the other interesting thing here is if we get up to the top of this table, remembering we were targeting around 240 to 250 kPa. Once we go to 260 kPa, you can see that we're actually putting timing back in. Instead of 32 degrees of retard, we're dropping that away to 28. So we can actually manipulate this table to kind of give us some boost control and get us onto our target. Essentially, if our boost climbs above our target, we just put timing back in, and that tends to reduce the amount of energy being provided to the turbo and brings our boost back down. So it actually can work really well. Now, more specifically, how do we get started? I've already mentioned that we do need to be really mindful of this strategy. It can be very damaging to your engine. We've got that ignition cut problem that I've already discussed. The two-step limiter also creates a lot of heat in the exhaust manifold. Cool aspect of it is it creates flames out the exhaust, and let's be honest, who doesn't love flames? But you do need to understand that prolonged use of a two-step limiter can be quite damaging to your turbo, exhaust manifold, even your exhaust valves. So proceed at your own risk. I always do recommend starting with no retard and see what boost pressure you've got. If the boost pressure isn't sufficient for the car to launch properly, then you can start adding small amounts of retard. Maybe start by retarding the timing 5 or 6 degrees. See what you get. If that's not enough, proceed in 2-degree increments until you get to your target boost pressure. This allows you to creep up on it without putting undue stress and strain on your engine. So there you go, quick insight into two-step launch control and how that can be used for a drag application. Our last question for this episode comes from Helsword, who's asked, I think it would be amazing to know how you can make a normal engine rev higher than stock safely, say a V8 that maxes out at 6,500 RPM. How do you make it go to 8,000 RPM plus? Good question there. And again, like a lot of these questions, there's a lot of complexities around this. It's a question I do quite often get asked, and there's a few other things that often are overlooked when it comes to increasing the RPM limit of an engine safely. First of all, just making your engine rev further in and of itself doesn't necessarily mean you're going to make any more power. What you'll find is that with basically every factory engine, you're going to find that by the time you get to the rev limiter, both your power and torque are dropping away quite significantly. And what this means is if we continue to rev the engine further, we're just simply going to continue to see our torque and our horsepower plummet. So just revving it for the sake of revving it further is not going to be particularly productive. And what I'm getting at here is in order to actually make it worthwhile revving beyond the factory rev limit, we need to make some hardware changes to the engine that are going to allow it to breathe at a higher RPM. Now, because you've mentioned a V8 there, I'll bring in an example here of the GM LS V8. Obviously, there's a variety of different guises here, but this is a good example of where in stock form we may find they've got a rev limiter somewhere around about 6,000 RPM. And again, just like I mentioned, by 6,000 RPM, the party's well and truly over. Power and torque are plummeting. However, the factory cam in the GM LS V8 is pretty pathetic. Swap in a decent cam with a bit more duration and a bit more lift, and you're going to find that all of a sudden, by the factory rev limit of 6,000 RPM, the power and torque is still increasing. Well, at least the power is still increasing. Our torque's probably starting to plateau at that point and fall away. So what this means is that now, if we rev the engine further, we can potentially make more power, and it's all dependent on the cam. Our own in-house project LS, we're revving to around about 6,800 RPM. What do you need to do in order to rev it to 6,800 RPM or potentially even further? The first thing we need to consider is the valve train. As we increase the engine RPM with the factory valve train, we're going to potentially find that we lose control of the valves. We start getting what's often referred to as valve bounce or valve float. Basically, the valve springs can no longer control the valves and they will float or bounce, and that can potentially be catastrophic, particularly if you end up with valve to valve or valve to piston contact. So that's our first point. We're going to need to upgrade our valve springs. Now, that'll probably go hand in hand with a more aggressive cam profile, as I've already mentioned, and that helps the engine breathe at higher RPM, making it worth revving it further in the first place. The next aspect is to consider our engine bottom end strength, and this is very dependent on the particular engine you're dealing with. Some engines will happily rev 1,000 or maybe 1,500 RPM beyond the factory rev limit. Others, if we go 500 RPM beyond the factory rev limit, we may potentially end up with an expensive bucket of bolts all over the dyno floor. We don't really want that to happen. So there are a few aspects here to consider. First of all, we've got the mass of the piston, and as the engine RPM increases, the amount of stress and strain being placed on the con rod starts to dramatically increase, and basically the forces involved increase at the square of engine RPM. So even a 500 RPM increase over the factory rev limit, it might not sound much, but it actually creates a huge increase in the stresses and forces involved in those being applied to components such as our crankshaft and our connecting rods. While every engine is going to be different, probably one of the key failure points will be the connecting rod, and factory connecting rods just aren't really designed to see massive increases in engine RPM. There are two forces being applied to the connecting rod and they're very different, so we need to understand those. I've got a boost line connecting rod here just to give you a little bit of a visual idea of what's going on. So the first stress or force being applied to the connecting rod, which most people can understand, as a compressor force. So that's trying to push the two ends of the rod together, and this increases as we increase cylinder pressure. It's the cylinder pressure acting down on the top of the piston being transferred down through the connecting rod. So that is a compressor force, and basically it's trying to bend or buckle the connecting rod in half. So that doesn't really get affected by our RPM limit. The other aspect, which is the one that is often easy to overlook, is the tensile forces involved as the piston goes past top dead center on the exhaust stroke. Now, when it goes past top dead center on the exhaust stroke, it's the connecting rod's job to slow the piston down, turn it around and start moving it back down the bore. And on the exhaust stroke, there isn't any compression from the combustion charge to actually slow the piston down. Instead, the exhaust valves are open and it's simply pushing the spent exhaust gases out through the exhaust valves. So here, the piston's still trying to move up and the connecting rod's trying to move it down. So basically, in this case, the con rod is trying to be pulled in half. The failure point often there is the rod bolts themselves, or depending on the rod, maybe we can end up with a rod failure just because it's not up to the task, but our rod bolts are often a weak point there. So really it all comes down to just making sure that our connecting rods are up to the task, and particularly if you're looking at a significant increase in RPM, it may be that moving to an aftermarket connecting rod is going to be an essential element. Now there are other aspects to consider there, and I can't go into every potential situation. We may find that the piston itself is too weak, and again, as the piston goes past top dead center on that exhaust stroke, we may find that we're having issues with the wrist pin bending, or even there may not be sufficient strength to hold the wrist pin in the pin bosses of the piston. And of course then there's all of the stresses involved with the crankshaft as well. But the valve train and the connecting rods would be the key two to consider there. So hopefully that answers your question. So that brings us to the end of this episode. If you liked what you saw, give us a thumbs up. If you've got questions on any of those questions, ask those in the comments and I'll jump in and help you out there. If you haven't already subscribed to our YouTube channel, make sure you do so. This way you won't miss any future updates. In our next episode, we're going to be jumping back to our Toyota SR86 build, and we'll update you on the progress with that and see where we're at, given that we're only about 4.5 weeks away from our first race meeting at this point.